you see here. Take another minute and think about what you see.
It's gonna be.
Okay, well, just like four, please. Raise your hand. Okay, Abby.
Snakes around.
Snakes around. What do you call that? What do you mean by snaking around? Like it curves. Okay, good. All right. When a river curves, we call that. Oh yeah, let's change the marker there. We call that a meander. A meander. Yeah. So kind of like, you know, we have meander and it kind of wanders and just kind of curves its way around things. And so each one of these is called a meander. So we have meanders here and here. Those are your meanders. Anywhere where you have that curve, you have a meander. And so we talk about rivers. Typically in rivers with low slopes. It's going to be really important here. We have this process called meandering, and it's typically going to be in a low slope environment. Okay, where you have very little elevation change from one point to the next. So you get a lot of meandering. Okay, what else do you notice? Go ahead, Madison. Where is the sand? On the corners. The meanders, right? Yeah, okay, so let's start using those terms. So we have sand here, and here, and here. Okay, so let's go over this one more time. So we have a meander right here, correct? And we have a meander right here. Okay, if the river is flowing in this direction, think about going on a little canoe trip. Where's the sand? It's on the inside. Interesting. How many of you guys have seen that before in rivers around here or just rivers in general? Have you seen the sandbars before?
Oh, yeah.
Okay. They're always going to be on the inside of the curve. They're always going to be on the inside of the meander. Now, what we call those are point bar depositions. And as we already said, they're always going to be where?
On the meanders.
We're at on the meander.
I don't know. On the inside.
On the inside of the meander. It's basically sand. It's a deposition. And we're going to talk about that here in a minute. What do you guys see that's happening here? Here, look at this shape. And this shape. What does it look like?
It don't look like it's grass.
You guys are missing this completely. Say that again?
Like a U shape.
Yeah.
Everything's shaped in a U. Like that.
Yeah.
Like a V. Like a V. Like
So what does that tell you?
that water. The water. Like
So this is the new sand right here, right?
Yeah.
So what is this?
Old sand.
So what does that tell you about the river?
It goes back.
What do you mean it goes back?
Like it keeps receiving that.
Yeah, it's actually moving slowly in this direction, right? Okay. This is actually a typical behavior. When you have that point bar deposition, rivers actually change their shapes. And they change their shapes very easily and very quickly. And when I say that, I'm not saying like within a year's time. Well, I'm saying within your lifetime, you will see significant changes in a given river. So it happens very quickly when we're thinking about geologic terms, Madison. So we can see when we're looking at this that the river is definitely migrating, where you have the original curve right through here, and this is basically sequential depositions that build up over time, and then the vegetation starts to build up on it, and then we're starting to get sand dunes. And again, we can see that right here as well. So, although on this side of the meander we're moving in this direction, what's happening on this meander? It's moving in the opposite direction. So what could possibly happen is our river start to have this really sharp turn to it. Does that make sense? Okay, so again, the rivers are going to migrate their channels. They don't always stay in the same place. Now another important point to make here is if I'm depositing on the inside, what's happening on the outside? Okay, so let's talk about this. So on Friday we talked about reaching equilibrium, right? Everything in nature is trying to reach equilibrium. And rivers are like an organism, like a living organism. And living organisms like to have full bellies. And so when a river reaches carrying capacity, that's what it's trying to do. It's trying to reach that maximum carrying capacity. It's trying to be full. Well, if I'm depositing some of that carrying capacity on the inside, I'm no longer full. So what am I going to do in order to reach that carrying capacity? How do I replace the sediments that I lost? I got to take more from the outside. So I start to erode on the outside. And we're going to talk about the physics behind that here in just a minute. So what does that tell you? I'm depositing on the inside of my turn, but I'm eroding on the outside of my turn. Where are you going to find those nice, wonderful swimming holes in the river? On the outside of the meander. And the outside is always going to have that down cut, and it's going to erode away at the outside of the turn. Now, let's talk about the physics behind this. This is a test question that I want to make sure you guys get, make sure you guys understand this. So, big star test question. All right? And it's very simple, too. The wording is really crazy, but it's a simple concept. Basically, you say, explain how the role of fluid dynamics works in the creation of point bar depositions. So lots of fluff basically says how are point bars made. Okay? So take a ruler or a meter stick. I know it's going to sound like really weird to you guys, but you guys remember vinyl records or know what I'm talking about when I say vinyl records?
Yes.
No.
Like
Not even close.
Oh,
Not even close. Like 50, like basically like 20s all the way up to the 70s, and then started going to 8 tracks in the 70s, and then you had cassette tapes in the 80s, 90s with the CD revolution. And now we're in the MP3 revolution. Okay? Which is funny, because MP3 is already called it all. Alright, so, I want you to imagine this. In fluid dynamics, all the points have to stay in a line. Have we talked about that before?
No.
Wait, I can't remember. Well, might be one of my mind here. So, as I'm in this river, imagine having a straight line going across the river. All those points have to stay together at the same time. So they can't like get bent out of shape. Okay, they're not going to do this. They have to stay in a straight line. So they're going to flow in a straight line. So in order to do that, as I'm going down the river, it's all fine and dandy going down straight. You can stay in our line. But what happens? Okay, think about marching band. What happens when you want that whole column to turn as one unit? Okay? Think about this. So here we go. We're going down the river, and I'm turning. Tell me what happens to the person on the inside.
It stays.
Kind of stay still, right? What happens to the person on the outside? Who has to move faster?
The outside person.
Why?
Because
You have a farther distance to go, right? It's like if you think about running the track. If you're on the inside loop of the track, you have a shorter turn to make. If you're on the outside, you got a longer turn to make. So therefore, the person, if you're going to do it in the same amount of time, it's still, when the time is over, still be in line. That means the person on the outside has to speed up, but the person on the inside has to do what? Has to slow down. The person on the inside slows down, the person on the outside speeds up. Okay? Think about the same thing with the river. I have this particle of water that's slowing down, but this particle of water that's speeding up, okay? So, what role does velocity play in carrying capacity? More velocity, more current carrying capacity. So again, if I'm coming around the meander, my inside slows down, so what happens to its carrying capacity? It drops, therefore all the sediments on the inside do what? Fall out of suspension. And therefore we get the point bar depositions on the inside. Does that make sense? So since I'm slowing down on the inside, I lose my carrying capacity, those sediments fall out of suspension. Now, the water on the outside speeds up. So what happens to that carrying capacity? It increases. So therefore, it increases the carrying capacity, which therefore increases erosion on the outside. Does that make sense?
Yeah.
Drake and kind of like I'm moving now.
I got him. Time. Pick up. Not me.
I got about 4 hours. All right, so. Oh, you guys are used to that? Not so much outside. All right, so that's going to be a really big test question. Somehow, I don't feel very good. All right, here you go.
Not really.
What don't you understand, Bree?
Like some. It's not mine.
What do you mean how it's made?
I'm saying like the wood.
Yeah.
Julia hit.
Okay, so Bree, I want to think about this. That river is full of sediments, right? Okay. So if I'm on the inside of the turn, okay, I've got all my sediments with me, and I'm coming around, I'm slowing down. So my ability to transport those sediments is dropping. So it decreases. So therefore, all those sediments in my column of water start to fall out of suspension. When they fall out of suspension, where do they go? They fall down to the bottom of the bed and build up over time. They get deposited. So what you're really seeing here, again, on a grand scale, you're seeing a deposition occurring. But what is really happening is being deposited one single granule at a time. You're just not going to see that. Okay? You're seeing it as a finished product on a grand scale. But what's really happening every second of every day, 1 or 2 more pieces of sand are being